We talked about heat transfer previously in general, but this is talking about how heat transfers through a window assembly, that being the whole part of the window, the glass or glazing, and the frame. So the conduction is primarily through the glass, although it can also be through the frame. Convection is air movement, and that convection especially happens in older windows where the parts don't meet so well, and so drafts can happen in between the sashes and the frame, also around the exterior of the frame. And then radiation. So radiant heat comes through glass and can come through the frame as well. Most of it is through the glass, as the glass is the biggest part of a window assembly. So the way we measure heat transfer and the terms that we use for heat flow for windows is the insulating value, which is called a U value. Sometimes it's called a U factor. And unlike walls, where we measure the R value, which is the resistance to heat transfer, in this case, we are looking at the insulating value, and there is a relationship between the two. 1 over R gives you the U value. And remember that the U value is always going to be a number of 1 or less, so a decimal. We also have heat gain from solar radiation, and that's measured with the solar heat gain coefficient. And we have air infiltration, which is measured in air changes per hour, ACH. The other considerations are the amount of visible light that comes in, the comfort, which is measured by the amount of low E that might be provided, and fading. If we have an ultraviolet light blocker, it's going to reduce the amount of fading that happens due to ultraviolet light coming through the glass. So looking more at heat transfer, I'm going to start off talking about U value, and the next slide will be about emissivity, low E. If we look at the image to the right, we'll see that we're looking at a diagram where outside is 0 degrees Fahrenheit, the temperature, very low temperature, and 70 degrees inside, and we have a multitude of different types of heat transfer happening through there. Typically, we're going to have more heat going out the window. If you remember, heat is trying to create that sweet spot where everything's equal. So our heat flow will be from hot to cold. And the little sort of dramatic looking hooked arrows are showing air, convective air. So the insulating value, U value, is a measure of the rate of non-solar heat loss or gain through a material or assembly. The lower the number is, the better. So a perfect insulator would have a U value of 0. We have not gotten to that point yet, certainly for windows. And the winter U values measured with the design conditions as noted on the screen. 70 degrees Fahrenheit inside, 0 degrees Fahrenheit on the outside. The U value is affected by a combination of conduction, convection, radiation. The large blue arrow represents conduction. The up and down blue areas arrows represent convection, and the smaller green arrows represent radiation, radiant heat. If you reduce any of these from transferring through, you reduce the U value. And if you remember, the lower the U value, the better. So now looking at emissivity, which is another portion of insulation. It's the ability of a material to radiate energy. The lower the value is, the better it is, because that means that less radiation is transmitted. When heat or light energy is absorbed by glass, it's either convected away by moving air or re-radiated by the glass surface. The ability of a material to radiate energy is called emissivity. Again, the smaller the number, the better. Long-wave radiation is the heat energy given off by objects with relatively low temperatures when compared to the sun, such as humans, equipment, light bulbs. Reducing a window's emission of heat can greatly improve its insulating properties. Clear glass, which has an emissivity of 0.84, absorbs 84% of long-wave radiation striking the surface of the glass and reflects the remaining 16%. It's one of the reasons why we don't get sunburns when we're inside, even if we're sitting in the sun. Those of us who do get sunburned. The thermal environment always is seeking equilibrium. In the winter, when it's cold outside, our bodies will radiate heat towards colder surfaces like windows, and we feel cold when the surface of the glass is cold. We feel cold when all surfaces are cold. If you have glass with an emissivity of 0.04 instead of 84, 96% of our long wave radiation is reflecting back into the room and therefore reduces the need for supplementary heating. Glass with a low emissivity will also have a lower U value. In the summer, so that's, we're seeing on the right hand side, somebody is radiating heat, and if there's nowhere for the heat to go, then you don't feel as cold. We're seeing a low E on the inside of the window, bouncing that radiant back to us. And in the summer, same thing, we would want there to be a low E coating that would bounce the light back to the exterior. Objects outside of the building, such as parking lots, black parking lots, and neighboring buildings, absorb heat from the sun and re-radiate it in the form of long-wave radiation. Again, glass with an emissivity of 0.04 will keep 96% of this long-wave radiation out of the building and thus reduce the need for supplemental cooling. The other things that we mentioned were the solar heat gain coefficient, which you read about, and which is part of solar radiation, of course. As solar energy passes through windows into a building, it is the infrared component that causes buildings to heat up. So infrared part of light. Light is visible, infrared is heat. The solar heat gain coefficient is a measure of that fraction of the incident solar radiation that actually enters a building through the window as heat gain. For example, a window with a solar heat gain coefficient of 0.41 means that 41% of solar radiation enters the building as heat gain. If you are interested in cooling, such as in a desert environment, a smaller solar heat gain coefficient is better. That means less solar heat is entering into the space. However, for passive solar heating, larger is better. We will be talking more about solar heat gain when we talk about passive heating, but it's important to keep this in mind as we move forward. The number that's listed, we've got a little blue arrow pointing towards this particular window that is a solar heat gain coefficient of 0.32. That number could be expressed as being tested at the center of the glass, or it could be for the total unit. The National Fenestration Rating Council requires a label on certified windows to show the total U value. So here we see the U value, which they're calling U factor, is 0.35. This doesn't actually meet code for Oregon, but once upon a time it did, and in a more temperate climate it would. Also, the total window solar heat gain coefficient and a visible transmittance. So we see here that the visible transmittance is at 51%, and that has to do with typically what happens is the more effective a window is at shielding from solar heat gain and low E coatings, it tends to decrease the visible transmittance. So if views and high transmittance are important, also this comes into play with daylighting. We tend to want a higher visible transmittance for those, but it will affect the some of the other items. So it's a little bit of a balancing act like so many other things are. Also, you notice the air leakage is listed here, and that has to do with the amount of air that can pass through the window assembly, and it is something that we aren't talking about quite as much, but something to keep in mind. Now I'm going to talk about low emissivity coatings, which are low E. In a nutshell, the UV light is reflected while visible light is transmitted. Also, infrared light is reflected. This is added comfort. If we look at this image right here, we can see it's especially glary outside, very bright, but inside it's not as bright, and these kids can happily play near the windows without being uncomfortable. So, how does low emissivity coatings work? Um, it makes the glass spectrally selective. It transmits visible lights while reflecting other types of energy. As we see here, we have an image where we're seeing two panes of glass, and the coating is on the inside of the exterior in this image, and we're seeing that as the sun hits, that we are reflecting out some of it and some of the light is still coming in. It has to do with what our goals are. If we see at the bottom, in warm climates, we want our heat to be reflected to the outdoors, and in cold climates, we want the absorbed heat to be conducted indoors. And we also see in this slide that they're calling out surface 1, surface 2, surface 3, and surface 4. So if you do end up specifying windows, it's good to understand this concept of the double pane and the four sides of the glazing and where that low E is going to be. If it's on the exterior, it's bouncing heat out, and if it's on the interior, it's bouncing heat back in. Now, the other reason why the low E coating has to be on the inside of all of this is that it's made from microscopically thin layers of silver. And if they get wet, if they're exposed to moisture, they will tarnish and be less effective, and also create that sort of speckly look that you might have seen in some older double paned windows. Also, we're protecting it from scratches, which would keep it from being as effective. The other thing I wanted to point out is quite often with a low E specified coating, we're going to see argon gas in between the panes of glass in our double paned or triple paned glass. Argon is denser than air, and because of that, it is better at reducing the conduction of heat through glass than plain air is. Air is a good insulator, but argon is better. And that means the whole window assembly will have a lower U value. And of course, lower is better when it comes to U value.